Welcome again to magnetostatic fields. Today we will discuss about magnetic field of a coaxial cable as an application for Ampere's law. So the problem states that magnetic field is required to be calculated for a coaxial cable with a current I equal to I naught in the direction of K4 in the inner conductor and equal to minus I naught in the direction of K for the outer conductor, and we are given description of the inner conductor having a radius of A, and the outer conductor have inner and outer radii of B and C. If we plot the cross section of this one, assuming that this axis is coming outside this slide, they say this is your inner radius, or sorry, this inner conductor, and now we are plotting the outer conductor like this. The inner will have radius A, the outer this inner conductor, then you have your outer conductor. The outer have inner radius of P and outer radius of C. Now we will notice that we have four different areas where we can calculate the magnetic field. The first area is inside the inner conductor. If your Ampere surface has rho, I mean the radius of the circle is less than A. The second area, when your Ampere surface has rho which is larger than A but still less than P. This area. In that case, this is easy. You will have I enclosed equal to the current inside this conductor, which is I naught. The third region occur when you are inside the outer conductor like this is your Ampere surface rho. In that case, portion of the current will be whatever inside here, which is I naught, and the other portion is what is inside this specific part of the outer conductor, which will be portion of the current density integrated over the surface. And finally, when you are outside here, you will have inside I naught and outside minus I naught, so these two currents will cancel each other and I enclosed will equal to 0. The question now, what is JS1 and JS2? And to do so, simply because this is a uniform current or a DC current, then you just need to divide the total current by the area enclosed. So in that case, you have I naught. This is the current inside the inner conductor, and the area of the inner conductor is nothing but area of a circle, which is pi a squared. And for the outer conductor, it is the same. You have a current equal to minus I naught, and you need to divide by the area of this, all of this here circle. You have two circles intersecting. The inner circle is area is pi b squared. This is the inner circle, and you have another area h pi c square is the outer circle. If you make minus of the two things and take pi as a common factor, you will get pi multiplied by c square minus b square, and you have here your current. And now if you want to calculate the total current in each case, this one is already done. Now when you integrate here, you will integrate JS1, which you just determined, and in that case you determine from 0 to 2 pi, and here you determine from 0 to rho, and here again you determine from 0 to 2 pi. This is your circle, and for the other one you determine from P to C. Anyway, let's follow and see how calculation will proceed. Before doing so, let's check back with Ampere's law. This is our Ampere law. Integration over a closed surface or contour of a surface, H del dl equal to I enclosed. And we need to understand that this is a symmetric structure. That's why uh, we assume also it extends for very long lengths in the axis, and the resulting magnetic field we will find it will be depending on rho direction, sorry, rho component, and it will only have a phi component. Based on this, you can rewrite this equation h dot dl equal to integration of what we have written here, h phi rho in the direction of phi and we are looping in the phi direction, means our dl, this is our h, but we didn't write our dl, so let's write our dl first, equal to rho d phi in the direction of phi. So we substitute here, you will get here rho d phi in the direction of phi. When you multiply dot product phi with phi, this will result in 1. Then you can rewrite this equation here as integration 0 to 2 pi, because this is a whole circle, h component rho d phi, and all of these are constant with respect to phi, so you can rewrite as these constants h phi rho multiplied by rho integration 0 to 2 pi d phi. With this one is nothing but 2 pi, that's why you will find that integration h dot dl equal to 2 pi rho h phi of rho. Now we proceed with the calculation of the field in each region. So for the first region, again, we first need to calculate the total current. So we already have Js. We substitute with its value. It is a constant, so we take it outside. We are integrating over area rho d phi, because z is perpendicular. Rho will vary from 0 to some value rho, and phi vary from 0 to 2 pi. This will bring you with 2 pi. This brings you with rho square over 2. Then you just make mathematical manipulation. You will end with I naught rho square over a square. Substituting the Ampere law, here is I enclosed, here is the result of integration h dot dl, and just mathematical manipulation, you will find that h equal to I naught rho over 2 by a square in the direction of phi. If you do the same for the second region, left hand side doesn't change, only right hand side change. You have here this time I naught divided by 2 by rho, you will get that h equal to I naught over 2 by rho in the direction of phi. So for the third region, which where rho varies from P to C, you will have enclosed current I naught. This is positive, and you have a negative I naught, but only a portion of it, which corresponds to JS2 integration from 0 to 2 pi and from 0 to rho, so from P to rho. And in that case, you will have the same integration. We take outside the portion of JS2 because it is a constant. Then you integrate again, you will have rho square over rho for this integration. This 0 to 2 pi is very easy. And just if you make mathematical manipulation again, finally you will reach this value. Then we add this result here, this result. We add to I naught here to calculate the total I enclosed, and do some mathematical manipulation. You can do this yourself. You will reach to this value. And once you reach this value, again, left hand side will never change because we are in the symmetric region. And then this is the resulting current due to our calculation for this I enclosed. Then you just make also mathematical manipulation by dividing by this factor 2 by rho. Then you get h equal to I naught over 2 by rho multiplied by c square minus rho square divided by c square minus p square. Finally, last case where rho is larger than the outer inductor outer radius. In that case, as we have said, we have I naught enclosed and minus I naught enclosed. They cancel each other, so your right hand side is 0. And due to this one, your final h will be 0. So the most important thing here is to understand how to calculate the current for the field. We assume it has a symmetric shape. That's why left hand side of Ampere law was very easy to calculate. Thank you.